So the first practical circuit we'll implement is an audio filter. And the reason for doing audio filters is something that you can actually plug into an amplifier and speaker and actually hear how it's working once we get it simulated and implemented. And for this, we'll use something that might be used in a audio mixer board where we'll have a low pass filter to remove any offensive high end. We'll also have a low pass filter to remove any perhaps 60 cycle hum that might be brought into your audio system. Now, although the flex analog works well in the audio range, understand that it also works up into the ultrasound range approaching a megahertz, has a good gain bandwidth product, and is very useful for a very wide frequency range. So let's start by placing a filter. So one tool that we have is the anodyne filter tool. So we'll start with that, and we're going to want to create a filter. So it comes up with a generic low pass filter, and this uses 2 stages. So this filter starts rolling off just under a kilohertz and is down 30 dB by the time you get to 4 kilohertz. So for audio, this is a bit aggressive, removes a lot of the audio frequency range. So let's just increase this to 10 kilohertz where we start rolling things off. And so I'm not sure why it didn't take there. Let me type in 10 kilohertz and hit enter. Okay. So the reason it didn't take there is because the pass band frequency was above the stop band frequency. So when you are changing things, you have to change them in the right order. So with the settings that we have here, let's see if we can go ahead and change the stop band frequency to be up here at 20 kilohertz. Okay. So now, because there's a big difference between the pass band and the stop band, it only needs one filter stage to achieve those specs. So now that the stop band frequency has been increased, we can increase the pass band frequency as well. Since this filter has a steep roll-off of 30 dB per octave, it requires 3 filter stages. So that's a bit steeper than we really need, and a bit steeper than you would see in your typical audio setup. We want to reserve 2 of the cabs for use in our high pass filter. So let's back off a little bit on the stop band attenuation. And by doing so, now that gets us back to a 2-stage or a 2-cab filter. And if we want to maximize that, we can play around with the values a little bit and just see where it kicks into a 3-stage filter. So at 24 dB, we're still good. At 26 dB, we've kicked to a 3rd stage. 25 dB, we're also a 3rd stage. So we can do 24 dB per octave and still only use 2 stages. So from there, we can now export this filter into Anodyne Designer. So we'll go ahead and send this filter to Anodyne Designer. And now in the background, you can see we have our filter. So 2 stages, only requires 2 cabs. They're both low pass filters, and these are the parameters that it automatically chose for this filter. So in order to wire up that input, we need to select one of our I/O cells, and it really doesn't matter which one, but we'll start with the one at the top, and we'll make this an input. So our options here are, of course, off, input, output, and independent amplifier. So an independent amplifier, that just means that this cell would not be used within the FPAA, but it would be able to be used for external circuitry. So we do want this to be an input, and at this point we can also set this up to be a bypass, which is a direct input, a sample and hold. So it will right at the input sample and hold the data based upon one of the clocks, or we can set it up as an amplifier filter. Now what this allows you to do is, using Rausch filter components externally, you can create a good low pass filter just using external components, and that allows you to remove a lot of the high frequency energy before it even gets into the chip. So before you do any amplification, you can remove offending frequencies even before you amplify them. So we already have a pretty good low pass filter that's being implemented. So for this demo, we won't use the amplifier filter. We'll just use a bypass input and just show exactly what the internal cabs are doing. But that's something that we do recommend that you use in general where possible, is these external Rausch filters both on the input and the output, as that allows you to essentially for the price of a couple of resistors and capacitors to get a very good filter that keeps the frequencies that you don't want in the chip from ever getting into the chip. So now these are differential, fully differential. So both inputs are brought in, and then this out, we just click on it and we're able to route it. The Anodyne Designer 2 software really likes to do its own routing, but you can't edit it once it's routed. So the best thing to do is click on the first point, click on the second point, and then once you've done that, you can now start to edit it. So you can find the dots that appear when you hover over it. So now you can move both the wire itself, and you can also move the label. So as long as you stay close to the wire, you can arrange things. So for example, here it automatically plays this N1 label where it's not visible, but we can make this visible by selecting that wire and then sliding this wire down, and now our label's visible. So the automatic connections get you to the place where the circuit is connected and you're able to simulate it and it's functional, but you can do manual cleanup to make the schematic more readable. Now, if we just want to look at this one filter stage, we'll start with looking at only the low pass filter. We also need to select an output. So we'll go ahead and enable this output. And when we have an output, again, we can have a bypass output, a single-ended digital output, or a mid-rail output. So we'll go ahead and bypass and look at the direct output. Now, when we look at this direct output, you will see some sampling that clock feed through on this, and later we will add some filtering to remove that. So again, we take our output of our filter and now wire it, manually adjust the wire and the label to the way we like it, and remember that although a single wire is shown, this is actually a differential pair, and internally these signals are fully differential.